Good afternoon, everyone, and welcome to this Tech Tuesday presentation brought to you by the Federal Privacy Council's Tech Training Working Group. I'm Richard Spidell, GSA's Chief Privacy Officer, and my co-chair for the working group is James Bird. James is the Acting Privacy Officer at the Cybersecurity and Infrastructure Security Agency, CISA. Our goal is to present timely, relevant technologies to our privacy colleagues, and we're very happy so many of you have joined us for today's event. I'm especially pleased to present our speaker today, Dr. Emily Shen, and I'm very excited that she'll be with us for the next hour. Dr. Shen is a technical staff member in the Secure Resilient Systems and Technology Group at MIT Lincoln Laboratory. Lincoln Lab is a federally funded research and development center, FFRDC, meaning it is a public-private partnership which conducts research for the United States government. Dr. Shen is a recipient of the 2019 MIT Lincoln Lab Early Career Technical Achievement Award, and she holds a computer science degree from Stanford and PhD degrees in electrical engineering and computer science from MIT. Emily's primary research interest is in cryptography. She currently leads projects designing and developing secure multi-party computation technology. I heard about secure multi-party computation at the FPC's annual summit in December, and I was excited about its potential, but I didn't get all of the technical requirements. I had a chance to hear Emily present, including more technical details about the platform she's developing back in February, and that's when my mind really started racing. What about potential applications in cybersecurity, human resources, as well as in regulated markets? During that February briefing, CIOs in attendance directly asked Emily if they could purchase her tool, which validated my excitement about its potential use within government. And that's why we've invited Emily to present to everyone today. And 3 reminders before I turn it over to Emily. Remember that we're recording today's presentation. Remember to please stay muted. And remember to use the chat window to submit any questions. I'll be monitoring the chat window and we'll relay the questions to Emily. So with that, it's my pleasure to now turn it over to Emily.
Great. Thanks, Richard, for the introduction and for inviting me to be here. And thanks, everyone, for coming. So I'm really excited today to talk to you about secure multi-party computation, which is a type of cryptography that can transform the way organizations share and process data. Specifically, this technology allows organizations to collaborate in a privacy-preserving manner without sharing their sensitive data. So let me start with some examples of what I mean by privacy-preserving collaboration. So one area where organizations want to collaborate while keeping their data private is for social good. For example, in Boston, there's a compact where companies agreed to measure the overall gender wage gap, but they need to be able to compute those statistics without any organizations having to share their own sensitive salary or demographic data. In the commercial sector, companies want to be able to collaborate for business purposes like pricing options or advertising while keeping their proprietary information private. And in the government space, organizations within the government or across multiple governments often need to collaborate in the interest of national or international security, but they also need to protect their secrets. So within the national security space, let me give a few more examples. In conflict zones, humanitarian aid organizations need to keep the locations of their sites private, and the militaries won't reveal the locations they're planning to strike, but it's critically important for them to deconflict and learn any locations they have in common so that the humanitarian organizations aren't hit. In space, international satellite operators want to hide the positions and maneuver schedules of their satellites, but they need to learn about any potential collisions with other satellites so that they can avoid an actual collision. And in cybersecurity, commercial I'm sorry, was there a question?
Oh.
Everyone, if you're not mute, please go on mute. We're getting some feedback.
Thanks. So in cybersecurity, commercial and government organizations don't want to reveal the threats they've observed on their own networks, but they all want to learn aggregate information about the threats they're collectively facing. So in all of these scenarios, we have multiple parties who, on the one hand, have input data they want to keep private, and on the other hand, need to collaborate to learn the results of some computations on all of their data. And as you well know, this problem has been recognized at the national level. National strategies and reports, and even recently proposed and enacted legislation have highlighted the need for privacy-preserving cryptographic technologies in general, and also for secure multi-party computation in particular, and that's the specific technology that I'll be talking about today. First, let's look at how people approach collaboration today without such technology. Say we have three parties with private data, and they want to learn about their combined data. Either they need to give their data to each other so that they can each compute the results, or they need to identify a trusted third party that they're all willing to give their data to and that they trust to compute the results correctly for them. But if the parties aren't willing to trust anyone with their data, not each other and not some external party, then they end up not sharing their data, and as a result, not collaborating and learning results. So today, to collaborate on their data, parties need to give their data over to one or more trusted parties, and this comes with real security and privacy risks. So imagine if we could replace this trusted party with technology. We'd need this technology to guarantee both correctness, that everyone learns the correct result of the computation, and security, that no one learns anything besides that result. And fortunately, we can actually solve this problem using cryptography. Specifically, there's a type of cryptography called secure multi-party computation, or MPC, that provides correctness and security without using a trusted party. And it's possible to use MPC to securely perform any arbitrary computation between any number of parties. MPC was actually invented in the late 1980s, but for a long time it was considered to be a purely theoretical construct. In the last decade or so, MPC has been implemented and it's becoming practical for many applications. In fact, MPC has been used for the Boston gender wage gap application I mentioned earlier. And at Lincoln, we've been working to make MPC development more practical for a variety of applications and applying MPC to national security problems. So in the rest of the talk, I'll first give an introduction to how MPC works. I'll start with a simple example and work our way up to how MPC is possible for any in theory. And then I'll discuss the practical challenges of building complex MPC functionalities and describe the software framework that we've built at MIT Lincoln Laboratory to address these challenges. And finally, I'll give some examples of MPC applications that we've prototyped using our framework. So how does secure multi-party computation work? MPC protocols work in 3 stages. The first stage is called secret sharing. So each party will take each of its secret input values and split it into a set of random values called secret shares and send one share to each party. Each party's share is completely random and doesn't reveal any information, but all of the shares together encode the secret input value. In the second stage, we compute securely on those secret shares, go from shares of the inputs to shares of the output of the computation. So to do this, the parties will decompose the overall computation into low-level primitive operations like addition and multiplication, and then iteratively compute each of those operations securely on those shares. All of these operations are done on those random secret shares, so no one learns anything about the intermediate results. And this stage is the bulk of the protocol and can involve a lot of computation as well as rounds of communication between the parties. At the end of the stage, each party then has a secret share of the output of the agreed upon computation. In the final step, the parties send those final output shares to each other and combine them to open the output of the computation. So let's see how all of this works with an example. Going back to the salary problem, say Alice, Bob, and Charlie want to compute the average of their salaries without telling each other their individual salaries. So they'll use MPC to compute the sum of their salaries and then just divide that result by 3. So concretely, let's say Alice, Bob, and Charlie have monthly salaries of 8K, 12K, and 10K, and they'll perform an MPC to learn the sum of their salaries, 30K, and then divide that result by 3 to learn that the average is 10K. So let's see how the MPC works. The MPC is for everyone to secret share their inputs, which are their salaries. And as a technicality, the secret shares will be with respect to a modulus. All the computation will be done using modular arithmetic, where here the modulus will be some value that's known to be larger than all possible values to be computed on. So let's say that Alice, Bob, and Charlie know that the sum of their monthly salaries won't be more than 100K, so they'll use 100 as the modulus. This means that all of the values in the computation will be integers between 0 and 99, and for any integers outside that range, we'll add or subtract multiples of 100 to get them to be between 0 and 99. So take Alice with her secret input 8. To secret share that value, she'll first generate a random integer between 0 and 99, say 16, and keep that as her own secret share. She'll generate a second random integer between 0 and 99, say 6, and send that to Bob as his share. And then she'll compute Charlie's share so that the 3 shares add up to her secret, 8, modulo 100. So she'll compute that to be 86, and that will be Charlie's share. And all 3 of these shares are individually random, but don't reveal any information about the secret, but together they add up to the secret. So Bob and Charlie will do the same thing and secret share their salaries, 12 and 10. And now the parties have shares of all of the inputs, and so they can start securely computing operations on those shares. So to do that, to securely compute the sum of those 3 secrets, first each party will add together their share of Alice's salary and their share of Bob's salary and get a share of the sum of Alice and Bob's salaries without learning what that sum is. And then they'll each add in their share of Charlie's salary and get a share of the sum of all 3 salaries. So at this point, they have shares of the output of the computation. And the final step is for the parties to open the output shares by sending each other their final shares and just adding them up, again, mod 100. In this example, the sum of the final shares is 130, which becomes 30 mod 100. So why did this work? Let's see why the protocol is correct and secure. So first, let's see why it gives the correct answer. We wanted the sum of the 3 salaries, and each salary is the sum of the 3 parties' shares of that salary. So we wanted the sum of those 9 shares. And instead of adding them up by column, which would have revealed the secrets, the parties each added up a row and revealed those values and then added those up to get the overall sum. Now let's see why the protocol is secure, meaning that no one learned anything about anyone else's input beyond the sum. Let's look at Alice's point of view. She knows her own input, 8K, and she knows the shares she created of her input. And she knows her shares of all of the values. So at the end, she learns the output is 30K. She also learns Bob and Charlie's shares of the output. And the question is whether she can learn anything about Bob and Charlie's inputs besides the fact that they add up to 22K, which she can infer from looking at the output and her own input. So if Alice has a guess for what Bob and Charlie's salaries might be, say 9K and 13K, that guess will define a system of 4 equations with 4 unknowns. And so there's exactly one solution to Bob and Charlie's shares that's consistent with her guess. And this would be true for any guess Alice made. And so this means she doesn't have any information to help her rule out any of the guesses. And the same argument applies to Bob and Charlie. So no one learns any information beyond the result of the computation and what's implied by that result. So that was an example of how MPC can be done for a relatively simple computation. It turns out that MPC can actually be used for any arbitrary computation. You can think of this as a function or a computer program, but anything that you might want to compute on a collection of data from multiple parties, you can actually compute using MPC without anyone having to give their data to any other party. And the way this is done is generally using MPC techniques for either arithmetic computation or Boolean computation. For arithmetic computation, the techniques describe how to securely perform addition and multiplication primitive operations over integers. And then we can actually securely compute any function by composing addition and multiplication together. For Boolean computation, there are techniques for securely computing XOR and AND operations over bits. And again, it turns out that we can then compose those to form any arbitrarily complex function. So MPC can be used to compute anything using either arithmetic or Boolean primitives. So what's left? Well, in practice, there are real challenges with building MPC for complex functions. So next I'll describe some of those challenges, and then I'll tell you about the framework that we've been developing at MIT Lincoln Laboratory to make the task easier. So the first challenge is that MPC primitives like addition and multiplication, or XOR and AND, are very low level. So it's hard to build complex functions directly on top of those primitives. To fill in that gap, we can't just plug in traditional libraries for higher level computations for 2 reasons. First, the MPC algorithms need to be what's called data oblivious, which means that they can't make decisions based on the values of secret data because the data is secret. And so we need to write our algorithms differently. And second, MPC algorithms need to be optimized differently. Communication is generally the performance bottleneck for MPC, and so we need to minimize the number of operations requiring communication. And in the case of arithmetic MPC, this means we need to minimize multiplications because those actually require communication between all of the parties. And in the Boolean case, we need to minimize ANDs, which also require communication between all of the parties. To address these challenges, Lincoln has built a software framework called RAMP for rapid assembly of MPC protocols. We're not the only ones to have built an MPC framework. There are several existing frameworks, but what we've focused on in our design is ease of development, flexibility, and generality. We've designed our RAMP framework in layers. At the lowest layer, we've implemented both arithmetic and Boolean MPC primitives. This is important because arithmetic and Boolean primitives are each more efficient for different kinds of operations. And on top of the primitives, we've implemented an extensive library of what we call MPC Gadgets, which are optimized data-oblivious algorithms for common computational building blocks. These gadgets abstract away the complexity so that we can prototype high-level MPC functionalities by composing those gadgets together. And across the entire stack, our software abstractions let us have multiple options for each type of computation. And we have evaluation tools that let us measure the theoretical and empirical performance of the various options so that we can choose the most efficient one for each setting. So put all together, our RAMP framework allows us to quickly prototype complex MPC functionalities. To illustrate our approach of decomposing high-level functionalities into gadgets, let me show an example of functionality that we've prototyped, which is a secure set intersection. Here, each party has a private set of elements, and they want to learn which elements are common to all of their sets without revealing any other information. We've built this for a cybersecurity application for organizations to learn about malicious IP addresses that they've all flagged, but the protocol is general and could be used for set intersection of any type of data. And so it turns out that the set intersection operation can break down into 3 high-level gadgets. We first securely merge the data from the different parties into a sorted list, and then we do a secure deduplication operation, and then we do a secure sort. And the way that these gadgets further break down is that the secure merge and secure sort are built on top of secure comparison, and the secure deduplication is built on top of a secure equality. And these lower level gadgets are then in turn built on top of either arithmetic or Boolean primitives that we have in our framework. So this is a much more complex computation than, say, the salary averaging example I showed earlier. But with our gadget abstractions, we're able to allow it to be implemented fairly simply. So we can write the set intersection MPC function in terms of just calls to those 3 high-level gadgets that I mentioned earlier, because our gadgets abstract away thousands of lines of code to make this to make it easier to prototype these complex functions. Just to give an example of the performance of MPC for this type of computation, we've evaluated it in our framework, and here I'm showing running time in minutes versus the total number of inputs. And we actually separate out computation that can happen before the data is known to each party in an offline phase, and computation that happens once the data is known, which is called an online phase. And so when we do that separation, then the running time after pre-processing is improved. And in this example, we were able to get results for 3,000 inputs in about 4 minutes. And I'll just note that this is just an example, that this is not specifically fully optimized, and for specific functions, it's often possible to do a significant amount of performance optimization. So that was an example of one of our functionalities in some of our gadgets, but our RAMP framework has an extensive library of MPC gadgets for a variety of functionalities. We have over 70 core gadgets in our library, including arithmetic and Boolean operations, fixed point arithmetic, equality and comparison operations, sorting and set operations, and linear algebra functions. And together, these gadgets allow us to easily prototype MPC for a wide variety of applications. So let me talk next about some of the applications that we've prototyped.
Emily?
Yes.
This is Richard. Before you go on, can I ask a quick question? On the slide in which you're showing the inputs and the performance, has your research shown any, I assume those inputs depend to some extent on the number of participants that are computing. Can you talk about that? Is there any research on the numbers of participants that you can share?
Sure. So in this example, we've run this as a secure 3-party computation, And the x-axis actually shows the total number of input values across those parties. So it's actually, so for example, for 3,000 inputs, it would be 1,000 inputs per party. But in general, the number of input values that each party has is independent of the number of parties involved in the computation. But in general, the running time will increase with the number of inputs and also with the number of parties, because the communication is all-to-all communication. So the more parties there are, the more time the communication will take.
Got it. Thank you.
Sure. Okay, so to give some examples of MPC applications that we've prototyped, for DHS S&T, we've built MPC to allow organizations to collaboratively compute cyber analytics without revealing their own threat data. So, for example, organizations might want to compute the intersection of their IP blacklists without revealing the IP addresses on their own lists. We've prototyped MPC for that functionality, as well as for clustering organizations based on the similarity of their cyber threats to determine which groups of organizations can maybe have the most benefit in further collaborating and sharing information. And we've incorporated these prototypes into a DHS-sponsored federated command and control research system. For DARPA, we've prototyped MPC for detecting coordinated attacks across organizations by quantifying similarities in network logs. We've also prototyped MPC for computing similarities in malware samples across organizations, as well as for computing a suite of general statistical functions that are commonly applied to cyber data, but could be applied really to any type of data. On a Lincoln Laboratory internal effort, we've worked on MPC for securely training neural networks for a biological task, specifically for a cancer classification task. And for Air Mobility Command, the air component of US Transportation Command, we've built an MPC solution for merging personnel data sets to enable the kind of analytics that they need to do without sharing PII. We've also had impact through publications and presentations. We've had several conference publications, as well as a magazine article and book chapter, and we've demonstrated our MPC work at DHS S&T cybersecurity showcases. So in summary, secure multi-party computation is a technology that lets people collaborate in ways that they can't today because they aren't able to share their private data. MPC can be used to perform any computation securely in theory. To make MPC more practical, we've built a framework for rapidly prototyping MPC functionalities, and we've applied MPC to problems in cybersecurity, as well as some other mission areas. And we think that there are a lot of potential applications for MPC, so we're very interested in exploring additional applications. We're also working to improve the performance and usability for a framework, and looking to ways to transition the framework as well. And if you have any problems that you think could benefit from this technology, I'd be very interested in hearing. So thank you very much, and I'd be happy to take your questions.
Great, thank you so much, Emily. That's terrific. So far, one question coming through the chat was, has this been used for fraud detection, for nefarious or bad IPs, for example? Is there anything more you can add on the DHS example you mentioned before?
Sure. So for DHS, we were prototyping MPC for a variety of analytics relevant to federated cyber defense. So this could be used for computations involving malicious IP addresses. I mentioned that one of the functionalities we prototyped was a set intersection, which we applied to IP addresses. So here, each organization has their own list of malicious or suspicious IP addresses that they don't want to share, but they want to learn what's also in other organization sets, which may give a stronger indication that those are indeed malicious IP addresses. So that's an example of a functionality. You can also do general statistics on related to IP addresses or other things from network logs. Hopefully that answers the question.
Great. And I think that's a particularly good example because as the privacy professionals on the call know, IP address is kind of one of those gray areas where there are good arguments to be made that should be considered potentially PII since it can be linkable to a person. On the other hand, it really only technically identifies a machine. So these are the kinds of emerging areas where this technology can be particularly useful.
Right. And just to be clear, the work that I mentioned that we have done for DHS is prototypes, and it's not a tool that has been deployed in practice for those cybersecurity applications.
Okay, great. So now questions are definitely coming through the chat. So let me take them one by one. The first question that came through says, I'm working with trusted computing for MPC. Can this be used for a variable number of players and with potentially millions of records per player? Player could range in the thousands. So that's kind of a scope and scale question, Emily.
Right. So yes, so definitely. So the examples I showed here were just for simplicity, small numbers of parties like 3. But MPC can be used the protocols can be used for any number of parties, 2 or more. Some parties are for only 3 or more, but they can be used for large numbers of parties. But of course, then the performance may become an issue. And there is some research on how to scale MPC so that using some different techniques so that it's more efficient for very large numbers of parties than it would be if you were to use these generic techniques that we've been talking about. But I'll mention that when you have a large number of parties who have private data, that doesn't necessarily mean that you need to have your MPC be done by a very large number of parties. So for example, you could have millions of parties who have private data and they don't want to share it with any they don't want to trust any party with that data, but you can outsource that computation to a small number of parties that are trusted not to all collude with each other. So if you can identify a set of 2 or 3 or 4 parties that people can trust will not all be in collusion with each other, then the parties that have the private input data can secret share their data to those, say, 3 parties, send those shares to the 3 parties, and none of those individual compute nodes will know anything about the data. And then those, say, 3 compute nodes can perform the MPC, and then they'll have shares of the output. They still won't learn the output, and then they can send shares to the party that's supposed to learn the output, or the parties that are supposed to learn the output. So I just want to emphasize that just because there's a large number of parties who have the private data does not mean necessarily that the MPC must happen between that same large number of parties.
Great. One follow-up question I have before I get back to the chat questions is, in the example you gave, if millions of parties have private data and they want to effectively outsource the computation to, let's say, 4 trusted parties, if 3 of those 4 parties decided to collaborate, would the information still be protected?
Yes, I just want to emphasize it wouldn't be 4 trusted parties. It would be 4 parties that are assumed not to all collude. So that's kind of the sense of the trust. But yes, depending on the protocol that you're using, for example, the Boolean protocol that I alluded to but didn't describe, that is secure against collusion of any number of any subset of the parties, as long as not all of them are colluding, because by definition, if all of them are sharing their information with each other, then they have all of the secret shares of each of the secret values. But if all but one of them are colluding, they still will not learn the underlying secret data.
Got it. And I apologize for misspeaking there. I shouldn't have said trusted
No
parties,
problem.
but you just have to, I guess you just have to find a way to ensure that one of the parties won't collaborate. That should be sufficient, right?
Right. And it doesn't have to be a fixed one that's specified. It's just that if you can assume that there will be, that they won't all collude, that there will be at least one party that's not in that collusion set, then you get security. And in the setting where you're not outsourcing the computation, but instead the parties who have the secret data are the ones doing the computation, that's very easy to achieve because, if all of the parties are colluding together, then they might as well have just given each other their private data rather than doing a secure computation.
Great, thank you. We have a security question in the chat next. To what extent does the security of MPC decline as the same users engage iteratively? In the case of the salaries example, to what extent can participants narrow their guesses if they interact iteratively over time?
That's a great question. So I want to separate a couple issues. So secure multi-party computation says that for any function that the parties agree to compute on the data, you can compute that function in a secure way, meaning that only the output of that function and whatever is inherently revealed by the output of that function is revealed. What that doesn't say, what that doesn't guarantee is that the function that you are choosing to compute is one that doesn't reveal a lot of information about the inputs. So, for example, in the example I gave, actually, which was a small example of 3 parties computing the average of their salaries, there's actually a lot of information there. We saw that Alice learned that the 2 other parties, Bob and Charlie, that their salaries added up to $22K. And that was inherent to learning the output and knowing her input. And similarly, if you were to perform that MPC and then another MPC between, say, Alice, Bob, Charlie, and David now to learn the average of their salaries, well, in combination, that would tell you then what David's salary is. So MPC is not about saying, what computations should be run between the different parties without combining their data. The technology is about taking a function that you've determined and agreed you want to compute, and computing that in a way that reveals only the output and, of course, what can be learned by that output and any other information that you have in the world. I hope that helps answer the question. So I just want to say that, it is an important consideration to think about, what computations are being done, and to keep in mind that because those are functions of the input data, they do reveal some information about the input data, but the idea is that we want to ensure that nothing else is revealed about the input.
Right. So I think this would be probably something that anyone who's thinking about MPC would have to discuss and consider at the outset of the engagement, right?
That's right. You'd want to consider, what are you computing? What is it that you want the parties to actually learn? What is it that the parties should not learn? And also, as the person asked in the question, you know, what are the other things that you might be computing on the data? Is this a computation that's going to be performed, say, many times with similar inputs, which in some sense you can think of as one, you know, sort of very large continuous function. But there are important questions there to consider when deciding what to compute under MPC and how to do it.
Excellent. I'm going to continue reading the questions, even though I can tell you can see them in the chat. The next one is the COVID-19 question. Is MPC being considered for COVID-19 exposure notifications when someone has tested positive for the virus but does not want to share that test result with a public health entity, but does want to get the benefit of sharing the result via the Google Apple API to, quote, tell the other phones that it might have been in contact with?
That's a great question. So this was not the subject of this talk, but I am actually involved in the PACT, or Private Automated Contact Tracing effort led by MIT, involving many institutions. And that effort, as well as many different efforts around the world, are about how to do the exposure notification part of the contact tracing process in a way that preserves privacy for all of the users involved, which includes the diagnosed individuals and the contacts of the diagnosed individuals. I think that, so these particular proposals don't use secure multi-party computation, and they're not about making it so that a diagnosed person is not even in contact with the health authorities or a public health entity, but rather how contacts of diagnosed people can detect that they were in proximity to someone who's been diagnosed and be notified without revealing any extra information, and also how the diagnosed people can protect their privacy. But we do envision that, you know, in general, the diagnosed people would, you know, they would get the test result and be in the health system to get that diagnosis, and then be authorized to upload the private information that'll enable the automated exposure notifications.
Terrific. Terrific. Okay, the next question is, what is the program specification language for the MPC functions?
So framework is a C++ software framework, and all of the code is in C++. So both the underlying MPC is implemented in C++, and the language for specifying those gadgets that compose your application is C++. We don't use a domain-specific language.
And the follow-ups to that are, is this open source, and what is the license?
So we plan to open source the framework. It is not yet open sourced, and we are working on completing some of the features that we would like to have before open sourcing the framework.
Great. The next question is, how do you archive the data for ad hoc research? Does that have to be done by the individual players?
So if I'm understanding the question correctly, the data is not, so the data is not made available to players to kind of query at will. Here, the model is that, you know, the MPC will happen. In order for the MPC to happen, the compute parties need to be in agreement on the fact that they're doing a computation and what function they're computing together. So we're not publishing a secure version of data that then researchers can go kind of query independently and as much as they want. Yeah, hopefully that answers the question.
Okay, the next question is, have you done work incorporating differential privacy with this?
So we haven't incorporated differential privacy in the framework, but that's a great question. So just for those on the call who may not be familiar with differential privacy addresses an orthogonal notion of privacy, orthogonal and complementary, while secure multi-party computation is about how can you perform a computation so that you don't need to have the inputs from the different parties actually given to any single party. Differential privacy is about saying, how do you compute something so that the output of the function doesn't reveal information about any one individual input item? So if you think of a database, for example, where maybe each row corresponds to an individual data, differential privacy would make it so that the output of a statistical query to that database would have some noise added to it. So it would not be the exact answer, so that that output doesn't reveal anything about any one person whose data is in that database. So these notions certainly can be combined, and there's some work doing that. And so you could use secure multi-party computation to compute a differentially private version of a function so that both the data doesn't need to be combined from the different organizations and the output is noised in a way that doesn't reveal too much information about any one data item in the whole set. But that depends on the functionality you want and whether that trade-off of having some reduced accuracy of the output for this particular notion of privacy is what you want.
Okay. And this question in a similar vein is, do you have an approach for securely generating randomized distributions?
So I'm not sure actually what the question refers to. We do use standard libraries for our randomness generation that's used for example, for generating the random secret shares.
It looks like there's a clarification asking, can you generate non-deterministic random numbers?
So we're not proposing any particular random number generation function. We're using, we're using calls to standard library functions that are providing the randomness. So our randomness generation is dependent on how those functions generate the randomness.
Okay, we'll see if there's any follow-up on that thread in the chat window. There was one additional comment or question that says, for each research pass of the data, all players have to be contacted and agree. No way for using the data for later research.
So yeah, sorry. So let me clarify a little bit my earlier statement. I think it depends on whether you imagine that the computation is happening between the parties who hold the private data, or between some compute nodes involved in this outsourced secure computation. If your goal is to enable this ad hoc research that I think the question was about, you could do that in some way by saying that, you know, the parties who had the private data will outsource shares of their data to some designated, 2 or 3 compute nodes. And those compute nodes would be the ones that respond to requests to perform certain computations on the data. So then when someone says, I would like to make this, query, say a statistical query on the database, then, those 2 or 3 compute nodes could approve it and then do a secure computation of the data to then return the result to the researcher. So that's something that you could do if that model works for your scenario. But I guess I'll just say that inherently for a multi-party computation, there are at least 2 parties involved in the computation, whether they held the original data or they're just compute nodes. And those two or more parties do need to be in coordination to know that they're doing a computation together, and this is the function they're computing, and they have the secret shares of the data because they need to be in sync in that way.
Great. Thank you for elaborating on that. I think we've addressed the questions in the chat window. I do want to encourage anyone else who might have a question to go ahead and type it in the chat window. With the couple of remaining minutes we have, Emily, would you be willing to talk a little bit more about the Air Force transportation example that you gave before? I think that that might be applicable to potential HR business use cases in the federal government.
Sure. So this is work for Air Mobility Command, and the problem that they had is that there's data held by different directorates that hold the different aspects of personnel and various other things that they want to perform analytics on. But they can't just directly share their data with each other because it contains PII, like social security numbers, and that can't be shared by policy, and for good reason. So the typical way that you would merge data sets would be to get the data sets together and then do a database merge on this unique key, say social security number or some other identifier for each person. And that can't be done if you can't share the data. And really, the goal is not to share the data. The goal is to perform these analyses of the data and learn that output. So we've prototyped, and we're in the process of building a solution for them that uses MPC so that each directorate to their own data, but as a result, what they get is a sort of combined data set that's been implicitly under the MPC merged on, say, the social security number, but that information is never revealed and it's not in the output. The output is just the combined data that will actually be used for the analytics.
Great. Got it. Thank you. Okay, the last question that I have, one just came in. So with our remaining time, why don't we address the one in the chat window? And then if you could, Emily, also give us a sense of maybe what your anticipated time frame for releasing it as open source would be. But let's do the chat question first. Could you talk a bit about what needs to be done on the front end by all of the parties to prepare their data for analysis through MPC? How can this type of coordination take place where you have many situations like confidentiality applying to the metadata as well.
Sure. So let me try to answer the first one first. The processing that needs to be done by the parties on their data before the MPC will depend on the specific application. So, for example, for the simple salary averaging computation that I gave, that doesn't require any kind of pre-processing on the part of the parties. They would just run the MPC software, which would start the step of secret sharing those values, and then it would do the computation. I guess it depends on what level the question is at. So, for example, the software, if it's reading in a CSV file of values and secret sharing those, then the parties would need to make sure to have put their input data into a CSV file, for example. For other computations where the input data is not already kind of obviously in, say, the numerical format or the binary format that you would want, there may be some encoding that happens up front, which in general also can be incorporated as the initial part of the MPC. So I guess I would just say that it's application dependent, and if the parties agree on what the type of data is and the computation to be done, then the software, the MPC software, for example, that we would write, would take that into account and take that data in that appropriate form and then transform it into what it needs to be to then be secret shared so that the secure computation can happen.
Right. So is it fair to say that as long as the parties agree on the format and the structure of the data, that's really all that's required at the outset?
So the structure and the format of the data is needs to be, well, it's sufficient for that to be agreed on, and then the MPC software would take data that's in that format and then convert it into secret shares. So just as an example, like IP addresses, those are written in a particular way, and then our software, encodes those IP addresses as 32-bit values, and then it does the sharing appropriately. But that process would look different if you were, if your input data were CVE values instead, or arbitrary strings.